Today is my pleasure to welcome Dale Leckie to our graduate seminar. This is going to be a great lecture, so I'm going to keep my introduction extremely short, so Dale will have lots of time for his talk, and we will have lots of time for question and answer after the talk. So for question and answer, please type in the chat box. We'll monitor the chat box and curate the questions from there. You can also feel free to speak up yourself, but we'll give priority to the questions that are typed in the chat box first after the presentation. So Dale has his bachelor and a master in geography, I believe, from University of Alberta. Is that correct, Dale?
Yeah, the bachelor's is, yes, that's correct.
That makes us very proud.
Me
and his
too.
PhD in geology from McMaster University. He was a practicing geologist and worked at both in the public and private sectors. And he is also adjunct professor at the University of Calgary. And right now he has just published a book called The Scenic Geology of Alberta, a roadside touring and hiking guide. I believe it's just published this April. And I have not yet seen the book in our library yet, but I believe it's coming. So just keep an eye on that. It's a very good book. I have one myself in my library, so highly recommend it. So without further delay, I will give the podium to Dale, and welcome, Dale.
Thank you very much, Tony. Thank you to the group for inviting me and organizing this. I love it. Hey, so what I want to talk to you about today is the Scenic Geology of Alberta. And I'm a geologist, a professional geologist. I have been all my career. And I've always been teaching people. I've been scientific meetings, taking people across the prairies into the mountains. Then I decided it was time to inform the public about how geology has made this phenomenally scenic landscape that we have in Alberta. And I've done that through 2 books, and this is the second book. So we'll step through Alberta. Towards the end, we're going to get to a section that could interest this group, when banks fail. Again, from a high-level touristic perspective. So Alberta just doesn't matter where you go in this province. It's just so spectacular. Here's Dry Island, Buffalo Jump. And on the right-hand side, these are all landslides. Wherever you go along our river valleys in Alberta, there are these large to small to giant landslides. So how we're going to address the talk today is the Scenic Geology of Alberta is a story about unbridled power. It's a story about drama. It's a story about glaciers long past, and it's a story about when banks fail. So some of the scenery of Alberta, if you go west of Edmonton to Sulphur Gates Provincial Recreation Area near Grand Cache, here's a water gap, an amazing amount of water and power of water is required to form this, erode this. Southwest Alberta, Pine Ridge Lookout, Rocky Mountains, Rocky Mountain foothills in the foreground, and then the glaciated landscape. Southwest Alberta again, looking into the United States, Chief Mountain Police Outpost, provincial, as viewed from Police Outpost Provincial Park. Just beautiful, stunning scenery. Writing on Stone Provincial Park, Ice and Ipey National Historic Site in South Central Alberta, right up on the border. Here in Edmonton, Terwilliger Park, there's Olesky River Valley Park, a meandering river point bar, erosional cut banks on this side in the foreground, right in front of you, and a flat glacial lake surface. Dinosaur Provincial Park, scablands and badlands creates this unusual and beautiful topography. Milk River Canyon, Southeast Alberta, probably in my mind, one of the prettier places we have in Alberta. Might even rival the Icefields Parkway between Banff and Jasper. Red Rock Coulee, south of Medicine Hat, it's been called a moonscape. Go a little bit east to Elk Island National Park, and it's a glaciated terrain to give you these potholes. And that's what we cover in, that's, just bear with me here. That's what we cover in the book. It's places like that in the in Alberta that we cover in the Scenic Geology of Alberta. So I cover most of the province. Where those red dots are places that I take people. This photo of the giant dinosaur bone was taken right there in Edmonton. Just think of an animal that had bones like that. In the book, I also included art, acrylics on canvas by the artist Brent Laycock, and he put a bunch of his paintings into my book. Jesus, sorry, my mouse is messing up on me. Also, there's watercolors, Lucy Carreau, LC Carreau. So put on your hiking boots, fill your car with gas. It's time to explore and learn how Alberta's most scenic sites were created. So we'll start. The Scenic Geology of Alberta is about unbridled power. So we're going to start here in Southwest Alberta. We're going to go to Waterton Lakes National Park. And this viewpoint, what you see at this viewpoint, you can see these mountains. They've been thrust from 140 kilometers away, and then they've been eroded. There's been 10 kilometers of material eroded from the tops of these. Then you've got the Rocky Mountain foothills in the foreground that have been glaciated. Waterton, the sediments at Waterton are 1.5 billion, that's with a B, years old. At the time, Southern Alberta was south of the equator. It was a hot and harsh environment, and there was much less oxygen in the atmosphere than we have today. There was virtually no life on Earth except for algae. So I say that algae ruled the world at the time. And these algae, they lived in the sea. There was nothing living on land at all. It was just algae in the seas. Algae are slimy. They've got a sticky surface. So sand and silt and clay are deposited on the surface, and the algae build up like this to form certain type of mass called a stromatolite. And that's what you see here. Here's a larger stromatolite from Waterton Lakes, but on the right-hand side is an example of a stromatolite or stromatolite field from Western Australia. There, it's on the coast, lots of evaporation. The water evaporates, the water that remains gets saltier and saltier, and this becomes a very harsh environment. There's no snails, there's no gastropods living here that would normally eat the algae. Think of a fish tank. How do you clean the algae away from your fish tank? Snails do it. So here's a modern example of these 1.5 billion year old cabbage-shaped features. So why am I showing you that? Well, those stromatolites, those algae, create the cliffs that we see throughout Waterton Lakes National Park, 1.5 billion years old. And, boy. So that sets the stage for Waterton. So now we're going to talk about the unbridled power. Here's a Google Earth image of Waterton Lakes National Park area in through here. And you can see that these mountains are markedly different than the mountains to the north, towards Banff, further north to Jasper. So let's take a look at those. So that mass of rocks originated 140 kilometers to the north, to the southwest. Mountain building pushed this mass of rocks from west to northeast when the rocks were deeply buried. And these rocks are about 7 kilometers thick. So just think about that, 7 kilometers by 140 kilometers by 40 kilometers. Just think of the powers that are involved. So those rocks came from the southwest, 140 kilometers away. They were pushed here. And then from about 60 million years ago to now, the mountains were eroded to give you the shapes that you get. So remember, they were deeply buried. They moved at millimeters to centimeters per year to get this position. And then there was 10 kilometers of erosion. This erosion is going to keep coming back as a common theme as the talk progresses. And as a result, you get this beautiful, spectacular scenery at Waterton Lakes. So remember, those mountains, 1.5 billion year old sediments, they were buried probably 10 kilometers deep, and then they've been eroded and uplifted. That is power. Consider the forces that were involved to do that. Here's the Google Earth image again. Let's take a look here at the Waterton River Valley. And so we're going to go south of the valley and look north. And I want you to imagine that thrust sheet. That's how that thrust sheet was put in place. And then remember, there was 10 kilometers of material above this that was eroded. And we get the landscape that we have today. So go around the corner, and there's the front of that thrust sheet. Rocky Mountain foothills, completely eroded away here. A different type of foothills than you have in the Jasper and the Banff area or east of those places. More on unbridled power. Let's go to Edmonton. You recognize this bridge. It's the low level bridge. 1915, there was a flood. And the flood went to the base of the low level river bridge at that time. The city was so worried that the bridge was going to be wiped out. They had the Canadian National Railroad put a fully loaded train car, boxcar on it to help it from not being eroded. That's extremely impressive. Think of the power that's going there. And we'll come back and visit the North Saskatchewan River a few times. Along this theme, think about unbridled power, but this is the other extreme. In Edmonton, at the park, here's Hudson's Bay Edmonton House. The other extreme, you had floods, 1915. Well, in 1796, the Hudson's Bay journals tell us that the rivers were so low that canoes were damaged. The canoes couldn't be used to transport furs and supplies, there being no water in the river. Beaver and buffalo populations were down that year due to the dry weather. And there were fires all around Edmonton House on both sides of the river. So just the other extreme of that flood event had occurred about 120 years before the flood. The Scenic Geology of Alberta is about drama. Here we're going to go, and we're going to go into the Rocky Mountain foothills, south of Calgary, south of Bragg Creek, and there's, in the mountains, a lot of these gravel ridges. And these gravel ridges, I believe, are related to the legend of the Lost Lemon Gold Mine, a story of murder and madness. So, and this gravel, cemented gravel, called a conglomerate, is called the McDougall-Seeger conglomerate. If you go to the Crow's Nest Pass, Highway 3, and there's a great place. You go to the parking lot and you can scramble up to the northeast. Right above the parking lot is this gravel, this conglomerate. There's a hike around the interpretive center, and it takes you right in the middle of these gravels. And therein lies the story of the Lost Lemon Gold Mine. There were two trappers, mid to late 1800s, Blackjack and Lemon. Well, Blackjack was killed by Lemon. Lemon became unstable. He wandered out of the mountains. He went into Montana to an area called the Tobacco Plains. He told a story to a priest. And then after that, the priest and other colorful people with colorful names like Lafayette French, King Bearspaw, John McDougall, and the Blackfoot woman, Cloudwalker, they all searched in vain for the gold. Sometimes they took Lemon with them, sometimes not. They never found the gold. They never found what they had discovered. There's said to be a curse discovered with those that explore for the gold mine: tragic deaths, fires, storms, serious illness. So if you look at the legend, some of the names that are mentioned are Dutch Creek, Racehorse Creek, Highwood River, Gold River, Old Man River. And up and down the Rocky Mountain foothills is where those rivers and streams occur. Well, we've been able to identify a series of 100 million year old river channels which drained from west to east. And that's where these gravels that you see in the pictures are from. And in those gravels, and the details don't really matter except they relate to the gold story, there's volcanic pebbles, there's igneous pebbles. So volcanoes up above the igneous rocks. Where'd they come from? East Central British Columbia. and associated where the igneous rocks are in outcrop are gold occurrences. This was the site of the Caribou Gold Rush in the 1800s. So the story is, the interpretation is, these volcanoes, these plutons were being eroded, and the gold was being eroded and carried about 400 kilometers from the west to the east to be deposited in these ancient river deposits up and down the foothills. Is there gold there? We've assayed it. If you go to the base of a cliff and you grab some of the material that's weathered out over time from the base, put it in a bag, take it down to the river, and you can find anywhere from 5 to 20 colors in every pan. They're not very big. You're not going to retire, but it's fun to explore for. More drama, the geology of Alberta and drama. The neutral hills, disruption in the prairies. Northeast of Calgary, southeast of Edmonton are these ridges that really shouldn't be here, you would think. It looks like Rocky Mountain foothills. If you look at a Google Earth image, you can see these hills. They extend for 70 kilometers from west to east. They're 120 meters high. One of Alberta's early explorers in the 1700s, he noticed them, Captain John Palliser, and put them onto his maps and in his report. So why are they there? Glaciers from the north. Glaciers pushed and thrust bedrock to create these ice thrust ridges. The ice would advance and then it would recede. It would melt back. When it melted back, there was other abandoned blocks of ice were left there, and that was reincorporated into next time the ice moved forward. And when the ice melted out, it left these lakes that we see here. There are the ridges. There are the ridges there. There are these old ice blocks that melted out. And if you're ever exploring this part of Alberta, Gooseberry Lake Provincial Park is a beautiful park. Why do I call this drama? Well, the neutral hills, where did the name come from? It was a territory to be shared by the Crow and the Blackfoot people, First Nations people. The area was great for buffalo. There were berries there, winter protection from wind, lots of firewood, poplar trees. However, the Crow and the Blackfoot were constantly skirmishing, fighting. The Great Spirit was upset by that. One night, it is said that he put his finger down on the earth and lifted up those ridges. The two tribes woke up in the morning and there was a ridge separating them. They walked on either side of the ridges to this gap between the ridges. They met and then they made peace. And therein lies the name, the Neutral Hills. That's an unattributed story on the origin of the Neutral Hills. Let's go back into Southwest Alberta. Wally's Beach, a hike within a lake Pleistocene landscape. So northeast of Waterton Lakes National Park. If you know Alberta, southwest of McGrath, St. Mary's River they dammed it and it's created a reservoir. So way in the distance here is the reservoir. During the summer, the water is high as the bottom of the slide, and it's a beautiful little beach, and it's another beautiful little park. You can see the reservoir. You walk out there a kilometer or two, and what you can find are mammoth tracks. That's what these are, woolly mammoths. They're up to 50 centimeters across. They found, the archaeologists, up to 500 of them. There are camel tracks. There are now antique horse footprints. There's muskox tracks there. So the interesting part about this, besides the tracks and the bones, is the archaeologists have also found butchered horses, butchered camels. They found stone tools with proteins on them. And those have been dated at 13,300 years ago. So early North Americans were hunting these large fauna at the time. Here's some of the bones, some of the tools that would have been being used. It was bleak at the time. It was a very bleak landscape. The ice had just, from the large Laurentide ice sheet, had just melted back, and this area was ice-free, but there were valley glaciers here. It would have been harsh and cold, windy all the time. Glaciers, like I say here in the distance, very few trees. It was steppe-like, low vegetation and shrubs. Here's Lucy Caryou's rendition of that, her painting. And I think she's captured the bleakness of it very nicely. More drama, dinosaurs perish, meteor impacts, and never-ending floods. Let's go to the Red Deer River Valley, Dry Island, Buffalo Jump for this. And Dry Island, Buffalo Jump, you'll go to one of these knolls that's like this, down towards the river. And the paleontologists have found bone beds, in this instance of Albertosaurus, a meat-eating dinosaur that eventually evolved into tyrannosaurs. They found 26 specimens in the bone beds there. They ranged in age from 2 to 24 years old. And they from that, the paleontologists suggest, well, perhaps this giant carnivore hunted in packs, which is really a scary situation. So why do we have these concentrations, these bone beds of these fossils? Well, if you go to Africa today, and here's Kenya, this is wildebeest trying to cross a river. Wildebeest are herbivores. They're not carnivores like Albertosaurus, but it shows you kind of how these concentrations would have occurred. They will try to cross the river. They will drop. They will drown. And you can see the carcasses of the wildebeest here. You can see the animals that are eating the carrion. And that is what would have happened with the Albertosaurus carcasses. And then the next flood comes along, picks up all the bones and carries it downstream to be deposited in a point bar. And that's how the Albertosaurus bones would be concentrated. More drama. 66.5 million years ago, a meteorite hit the Earth, 20 kilometers across. It created a crater in the Yucatan Peninsula, 200 kilometers across. And if you go up and down the Red Deer River Valley, you can see that instant in time where that dashed yellow line is when the meteor hit the Earth. If you go downstream a few kilometers, there it is right there where that color change occurs in the photo in the lower right. And geologists have recovered iridium, which originates from space, as well as shocked quartz from this interval right here. Now, a meteor hitting the Earth is probably the most cataclysmic thing that can occur. When this one hit, there were giant fires just instantly. Darkness prevailed from the ejected debris and soot from those fires. There was nitric acid rain, and then sulfuric acid aerosols from the impact cooled the Earth. It was nuclear winter. And then that was followed by extreme CO2 levels, causing intense global warming. When the meteorite hit, 76% of all species died. It was a cataclysm. Let's look at glaciers. The Scenic Geology of Alberta is about glaciers long past. Here's ice thickness map of Alberta and across Alberta. The ice was up to 4 kilometers thick, 3.8 kilometers up in the north, thinning southwards. In Edmonton, about 3 kilometers of ice covered the city. If you run a cross section from north to south, you can see the ice being thick in the north, thinning southwards to the Alberta-Montana border. You can see the topography. The landscape rises from north to south. The ice actually flows uphill because of the profile shape on top, which is kind of interesting. So the ice was at its maximum, we'll say 22,000 years ago. All of Alberta was covered except for these areas here, which are called nunataks. They would have just been sticking up above the ice. Then the ice started to melt about 15 to 17,000 years ago. 14,000 years ago, there was an ice-free corridor here, and Edmonton is just about to be deglaciated. Remember this, we'll come back here. 13,000 years ago. By 10,300 years ago, the ice was gone. So what did that ice do? Well, south of Calgary and along the Rocky Mountain foothills, south of Hinton to the Montana border, are these giant glacial erratics. What happened? Why are they there? So this is the Okotoks erratic, south of Calgary, city of Okotoks, just a little bit west of Okotoks is where this giant block is. And it is truly a giant. So what happened in Jasper on Mount Edith Cavell, there was a landslide. A landslide took place and deposited probably hundreds of millions of tons of debris onto a valley glacier. That valley glacier flowed north out to the foothills, bumped into the Laurentide ice sheet, which was up to 3 kilometers thick. Therefore, the valley glaciers were deflected south, and debris was transported all the way south to Montana. And that's what gives us those giant blocks. There's Mount Edith Cavell, and those blocks are a distinctive type of quartzite. That's about 500 million years old. And we know that it came from Mount Edith Cavell based on the rock type and tracking them back up into the valley. Does that occur today? Yes, it does. Here's an example of the Alaska Range in Alaska, big landslide, probably because of earthquakes, onto the glacier, another one here, and then that debris is carried out, just like it is here in this example I'm showing here. Glaciers long past. Let's look at Edmonton. Here's a Google Earth image of Edmonton. It's dissected by the North Saskatchewan River. Well, Edmonton is built on a glacial lake bottom. It is such a flat landscape. That's because it's this old glacial lake with up to about 15 meters of silt. Because of this silt, it's great for building tunnels and the rapid transit system in Edmonton. I think that's so impressive compared to our other cities. And then the city, the area is dissected by the North Saskatchewan River, meandering and deep. So why has the river so deeply incised? Well, remember, there was about 3 kilometers of ice here. The ice melted. That's a tremendous weight on the prairie landscape. The landscape lifted up. And as the landscape lifted up, the river down cut. That's much like the erosion that takes place in the Rockies. When I told you that Waterton there was 10 kilometers of erosion, it doesn't mean that Waterton was 10 kilometers, sorry, the mountains at Waterton were 10 kilometers higher. No, when the erosion takes place, isostatic rebound lets the mountains lift up. Just like a melting iceberg off the east coast of Canada. As the top of the iceberg melts, the iceberg rises up. The same thing with our prairie landscape here. When the ice was starting to melt back, there was ice on 3 sides of the city at least, and it was just pouring water into here. Glacial Lake Edmonton formed. And then the lake started to drain initially south of the city, Gwynn Channel towards the airport. And then that became abandoned and the city started to drain northwards, taking its present position. The lake drained northwards, creating the valley where we get the North Saskatchewan River Valley now. Go to Terwillegar Park and you can see this flat landscape. That's your flat landscape. Here's the entrenched river valley from the glacial uplift. Before the Edmonton River Valley had been cut, there were older river valleys. Here's an old river course, at least 60 to 25,000 years ago. The North Saskatchewan River occupies that river course in part for part of its course, but a lot of these gravels provide the aggregate sand and gravel that's mined, taken out of the ground in the Edmonton area. So this is a pre-glacial river valley that flowed in Edmonton. Again, you go to Terwillegar Park, go to the end of the little point bar and look across the river, and you can see bedrock. You can see the sands and gravels from that old river system, pre-glacial river system. And then there's the glacial deposits there. At the time, and after the ice melted, there were these large panthers that were that were hunting in the Edmonton area. Edmonton was covered by 3 kilometers of ice. Deglaciation and uplift took place in the last 21,000 years. And the ice probably left Edmonton by about 14,000 years ago. Let's go a little bit. We'll come back there in a little bit. Let's go to Elk Island National Park, east of Edmonton. And it's got these low-lying hills, shallow wetlands, shallow lakes, lots of wetlands. During the last glaciation, ice would stream a little bit faster on either side of the area where Elk Island National Park is. This was a subtle little highland. So there's Elk Island National Park, east of Elk Island, the ice would stream, and in the Sherwood Park area. And if you run a cross section from southwest to northeast, across that area, you can see Elk Island National Park is built on a subtle little high. And then when the ice was melting, a giant block became isolated and stagnated right there. And after that ice left, we had this terrain, the Cooking Lake moraine, this glacial moraine all through here, which is markedly different from the landscape to the east and to the west. Geologists have all sorts of different names: prairie mounds, rimmed ridges, ice-walled lake plains, prairie donuts. The names don't matter, but they're descriptive. And it's great waterfowl terrain, and beavers love it. Briefly, let's go to Cold Lake, northeast of Edmonton. 99 meters deep, it was covered by 3 kilometers of ice. During the last glaciation, the ice actually pushed and excavated debris, once when it was flowing in this direction, then another time in this direction, to create that extremely deep lake. The next photo is from 30 kilometers south, a lake called Muriel Lake, and you can see the debris that's been pushed from Cold Lake 35 kilometers to form this landscape, this hill here. And Muriel Lake in itself is another ice thrust lake. Characterized, you can tell them they've got long straight shorelines, very, 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 very steep banks. There's a few other criteria, but those jump out at you. So let's deal with when banks fail. We're going to go to Edmonton again, North Saskatchewan River Valley. We talked about how it floods. We talked about how it dries up. We talked about how deeply incised it is. Well, it's the incision which is important for this part of the story. The North Saskatchewan River is a meandering river. So it erodes on one side, shown here, where I've labeled erosion, and it deposits here. These point bars, sand and gravel point bars. Historically, they were gravel pits. Then they were made into municipal parks. They've been made into golf courses. And again, parks that we see in through here. So the story here is you get erosion on one side, you get erosion here. You get erosion here, deposition here. So what happens is the river, the North Saskatchewan River, flowing in the easterly direction, undercuts this deep, steep banks. There's volcanic ash in the bedrock. Volcanic ash is extremely slippery. Basically, everything will slip on it so easily when it gets wet. There's groundwater seepage has weakened the hill slopes as well as the undercutting. Residential development, so homes, people watering their lawns, water percolates down. There's old coal mines. There's more than 100 coal mines along the Edmonton River Valley, and that's allowed access for water as well as to weaken the bedrock. So an example of that, well, here's some bentonite. It's not a very thick one, but thicker ones like this could be and are attributed to be the slip surface for some of those landslides. The one that I like and talk about, but there's several of them in the city, is Keillor Point. Here is Keillor Road. This used to be a road which went right through here. We've got bedrock and glacial thrust bedrock. River erosion. Because of the undercutting, there was a down drop block here, 1989. There's another down drop block that took place here in 2002. The city tried to remediate, prevent the damage, so they put in these great pylons. Well, it didn't do the job. Keillor Road is gone. There's the pylons, there's old Keillor Road. And you know, sometimes you just can't figure out Microsoft. You can walk down, there's in Belgravia, a nice little park, and this is built on those pylons, and you can see the slump, you can see the slides, you can see the point bar across the river. Go a little bit further east. Let's go to downtown Edmonton. So there's downtown Edmonton, Louise McKinney Waterfront Park. Why would the city make such a large park in such an expensive, potentially expensive area? Well, that's all landslide in through here. 1900s, 1900 more or less, cracks started to develop at the top of the Edmonton, North Saskatchewan River Valley. And then 1910, there was major displacement, down drop block, and all these slump blocks in through here. The city backfilled this hole. They backfilled with the green material in through here today. And then they put erosion prevention material in the park there. So basically, that part of the city is at high risk to landslides. The city built this beautiful park. Because if damage occurs here, it's not going to be extensive. This is to be a movement tolerant building. Here's the extensive riprap in through here. Let's leave Edmonton and go north. Just show you a picture. Here's the Peace River. I worked extensively along the Peace River Valley throughout my career, and it seemed wherever you went along that river valley, wherever the Cretaceous marine shales were, we always had slumps. This is at the town of Peace River. On the Peace River, the Smoky River is here, and wherever I've labeled S is a slump. It's a landslide. It's just absolutely amazing. I always described this river valley as being in motion on its erosional side. And there's just a cartoon from the Alberta Geological Survey showing some of the slumps, and they take place either in the Cretaceous marine shales or glacial lacustrine deposits that are within the river valley. Crow's Nest Pass. Not really bank failure, but still fits the theme. April 29th, 1903, Canada's largest landslide. It took place, it blocked the railroad, it blocked the highway. Half the town of Frank was destroyed, and at least 90 people were killed. The reason it took place was folding of Devonian and Mississippian bedrock. So if you fold rocks, bend them in half, they weaken. Basically, tension occurs on top, weaken those rocks. And then there was thrusting, where those red lines are. There is potential that coal mining at the base of the mountains contributed to the Turtle Mountain, to the Frank Slide on Turtle Mountain. And this area has been glaciated many times in the last 2.5 million years, which would have oversteepened the mountain. As a result, you get the Frank Slide. Did you know that mountain building in the Rocky Mountains has come to an end? Those majestic mountains that we know and love, they're wearing away. Why are they wearing away? What's happening? There have been multiple glaciations in the last 2.5 million years. Rock falls, talus slopes, landslides, debris flows. At least 20 kilometers of material have been eroded from the tops of the mountains in Yoho National Park. In Banff and Jasper, it's about 7 kilometers. Let's go to Yoho. Here's Cathedral Crags. Remember, 20 kilometers of erosion here from rock falls, talus, debris flows, glaciation. And what happens is we get this debris eroding, coming down into the river valley at the base of the slide, and we get isostatic rebound, we get uplift. It's just unstable, precipitous cliffs there into the river and into the Pacific Ocean. So the erosion of these mountains creates natural hazards. So let's take a look at the debris flows in the Kicking Horse Pass. So 2 debris flows coming off Cathedral Mountain, Cathedral Crags, as well as the one coming off Mount Stephen. Next photo, we're going to deal with the one coming off Cathedral Crags. And what you can see, there's Cathedral Crags. Right at the top of the slide is a glacier. You can see a gulch where the debris comes down, comes plummeting down, crosses the railroad at the spiral tunnels, crosses the railroad here as well. Sometimes if it's a big debris flow, it crosses the highway. What happens at the top? Well, there's the glacier, and you can see the vertical cliffs. You can see the loose debris. You can see how unstable it is up there. So the story, the interpretation here put together is that during summers, snow melt, glacial melt, there's lakes that build up on that ice, on that glacier. Eventually, there's so much water builds up that the ice lifts off and the water escapes. And you get a large volume of water taking that debris down slope. It takes it down the mountain, side of Cathedral Mountain, crosses the tracks a couple times, the train track, the Trans-Canada maybe, and maybe even the 3rd tracks. Let's take a look at another debris flow there. Let's look at the one coming off Mount Stephen. So here's Mount Stephen, and the interesting thing here, you can see a debris flow chute coming off the mountain. You can see Canadian Pacific Railway, grain cars, and the Trans-Canada Highway. There's a viewpoint where you can see this, where you can see Cathedral Crags, you can see Mount Stephen, you can see the debris flow, how the engineers have trained it with these artificial levees to keep it in path here. And then the railroad has built this tunnel for further protection, which is good. Sometimes it'll make it to the Trans-Canada Highway, sometimes it will not. So the Scenic Geology of Alberta is a story about unbridled power. It's a story of drama. It's a story of glaciers long past, and it's a story of when banks fail. And that all contributes to see that spectacular scenery that we've got across the province. I'd like to acknowledge the Canadian Geological Foundation and the Alberta government. I received a grant from both of those organizations, government, to prevent the book or to publish the book. If you're interested in the book, you can buy it locally. It's in Audrey's Books, downtown Jasper Avenue. It's in the bookstore in Perron in St. Albert, and Chapters Indigos covers it. So thank you very much for your time.
Hey, thank you, Del. The presentation's very interesting, and we have a good flow of questions coming in. So the first question is, based on the variation in the cover thickness of the Laurentine ice sheet over 10 or 20,000 years ago, will this explain why the clay or fines or even the organic content in the glacial tail deposit increase the more north and the more east you head in Alberta?
I want to take a look at chat. I got to make sure. Sorry, I'm just reading that chat.
Yeah.
I don't have for sure the answer to that, but I'm going to, as you go in the northern half of Alberta, we are covered by the Cretaceous bedrock is mostly marine shale. I showed you a bit of that marine shale when I took you to Peace River. So that marine shale is easily eroded, and that would contribute to the clay content in the till. And as you go further south, the clays are still there, that it's still marine shales, but we start to pick up more sands and other types of deposits. So again, not my field in detail, but I believe, basically the content of glacial till reflects the material upstream and just upstream. And that's why there is that higher clay content. So.
Thank you, Dale. I guess a follow-up question would be on the isostatic rebound, especially for areas where you have multiple glacier advance and re-advance, retreat. Are we going to see the isostatic rebound in those regions less prominent than the areas where there's only maybe a single episode of a glacial retreat?
That's kind of interesting because Edmonton might have been affected by 2 glaciations over time. Calgary was only affected by 1 major ice age. There was glaciers in the east of Edmonton, as well as the Laurentide ice sheet, from the mountains. And I'm talking over the last 2.5 million years. We don't have good evidence that there was 2 in Edmonton. So basically, if you go to Cold Lake, there is evidence for 2 icy glaciations. But okay, so the early glaciations would have caused, and I don't know if I'm answering the question properly, the early glaciations would have caused the subsidence. It would have started to rebound again. And then a subsequent glaciation would have caused the subsidence again, and it would have been cumulative. Alberta is still being uplifted from the last ice age. And remember, the glaciers left Alberta 10,000 years ago. There are parts of Alberta are still uplifting, and in the southern parts, because it's on the amount of uplift is varies, there's actually subsidence going on. So we've got uplift, we've got subsidence. It's an extremely complicated stories which the geophysicists work to understand and help us with. And I got those thickness maps based on work coming out of the University of Toronto, where the scientists were trying to understand the amount of isostatic rebound that took place. Great question.
Yes, I guess my follow-up to that is question is that it's very difficult to find any outcrops or even from the boreholes to kind of understand this rebound without more extensive studies, I guess. It
is so difficult to do because you can study glacial rebound, isostasy in the Arctic by finding ridges and beach ridges and dating them with bones and stuff. But in the prairies in southern Canada, we cannot do that. And so it's up to the modelers, largely. The geophysical modelers.
We have more questions. So this question from Kevin. So he went to Waterton Lakes National Park this year, and he was surprised by how quickly the mountains just sort of pop out of the ground. So could you touch a little bit more on their formation being pushed in from the west toward the northeast? Is this due to a tectonic plate from the North Pacific Ocean?
I got to think about how to answer that. Just let me think. Just give me a thought.
Sure.
Yeah, they do sort of pop out, and it's just like when you go west to Calgary and you see Mount Yamnuska, and it's like when you go west of Edmonton into Jasper, they just kind of pop up at you. But that's where that's occurring, and I'll say where those pop-ups are. That is where the older bedrock, in the case of Waterton, it's the 1.5 billion year old erosional resistant ridges. Remember, there's been 10 kilometers been taken off the top of that. In front of those ridges at Waterton, it's Cretaceous shales, marine shales, which are very easily eroded. And that is why it seems that I really like what you just said. Looks like they popped up, but actually they would have been almost the same, but because of the differential erosion of the marine shales, that it looks that way. So it's largely related to erosion. I hope that answers your question, Kevin.
Kevin, feel free to speak up if you want to follow up.
No, I think that was great. I think that hit on the hit the nail on the head there. Thanks, Dale.
Okay, so next question is about those glacial lakes formerly Edmonton. Cherry asked, I wonder why those lakes formerly Edmonton did not dry out through evaporation after the ice sheet receded. I think that's the question. And
it's going to be two words, and it's not the ones you're thinking of. It's too cold. You know, basically the ice is melting back. You could see, if you remember that map I showed you, ice all around the lake, and it's so cold there. Those of you who have been to the Columbia ice fields and walked out, taken the hike, you can feel the cold katabatic winds blowing off the glaciers, and the blowing winds would have contributed to evaporation, but it was just too cold to have high rates of evaporation. And so one of our story for Alberta is that all across Alberta, when the ice was melting back, lakes formed up against the glaciers, and those lakes catastrophically drained to cut deep valleys. You know, if you're driving across the prairie and you come across a big deep valley and there's no river in the bottom of it, it was probably cut by a glacial meltwater channel from when these lakes catastrophically drained. So too cold, I would say, for the evaporation you're suggesting. Great question.
Dale, when you say catastrophically drained, are you talking about a one-day event, that sort of event? Just the dam breached and the water just outburst, or is it difficult to tell?
Days to weeks, probably.
Days to weeks.
Yep. You know, you would start and then just sort of, you would build up intensity. The lake would be filled with all sorts of giant, coarse ice crystals, you know, material calving off the glacier, floating in the water. And then that would all contribute to erosion. So I'm going to say days to a few weeks.
That's very fast, geologically speaking, I think.
It's instantaneous, yes.
Yeah. Okay. I asked this question during your talk at the Edmonton Public Library, but I just want to ask again so everyone can hear it. For the the Cretaceous, the KT boundary, where that extinction event happened, possibly through a meteorite.
Hold it! Don't say possibly.
Possible. Okay.
Go ahead.
So my question is, can you suggest any outcrops we can easily hike to or visit to actually perhaps touch that with our hand, or just instead of going to the Drumheller Museum and see it from there? Or because I saw a photo of that KT boundary in your presentation slide with the the scale and is there
it's so difficult to go put your finger on it. The two pictures I showed in my talk, you can see it and you know it's at the base of the col, but it's very difficult to climb up there. At least, you know, it's hiking in Badlands terrain or topography can be pretty difficult. That's a steep cliff. The other one was on private property. It was a farmer's field. And so we had to get permission to go on there and to go see it. And so did the geologists that had done the research. There is one place that I remember seeing about 20 years ago along the Old Man River Valley. And I've never been able to find it again. And it's where the Old Man River Reservoir is. And a friend of ours took us there on a field trip. Those are about the only places I know. Most of them, Tony, are inaccessible in the province. The best one is to go to that one at Dry Island, Buffalo Jump, hike in and find that spot I show in the book and say, there it is there. If you're feeling brave, you might be able to, I say it tongue in cheek. You might be able to find a way to get up, and you right at the base of the pole, you look for that, and if you and dig away with a shovel. No, you're in a park, don't dig.
Right.
You get in trouble,
Mhm.
but look for
Yes.
that color change, and that's it.
So it's very, it's not that easy. It's not something that you can identify with binocular. Maybe not.
No,
Okay, so you have to either peel away or look really, really close.
yeah.
Okay,
I love your interest in asking that question because it is so important to our history.
that's right, because I saw every time I've been to Drumheller Museum a couple times, and I always see that KT boundary display.
Yeah,
It does seem very obvious from the display, but I always wonder where I can find it sort of in situ in the field.
it's really difficult. It really,
Right.
honestly, and I'm not trying to hide it. If I could find you a spot where you could go, I would tell you where you could.
You would
safely
update
go.
the book.
Yeah, yeah. Well, if it was there, yeah.
Awesome, thank you. Okay, I don't see any other question in the chat box. I think that's a wrap, and this is a great talk. Again, thank you so much for the presentation.
Thank you very much to the group.
Thank you. And this is our last graduate seminar for the semester. So we'll start again next year. So thank you everyone for attending those seminars, and we appreciate your support.
Hey,
Thank
thanks
you.
a lot.
Thank you, Dale. Thank you guys for joining us during the semester, and see you guys next year. Have a joyful holidays. See you guys. Bye-bye.
Take
Okay.
care. Bye.
Yeah, bye-bye.